So is the sound fine? Yes? Okay. Good. So let's go for the second lecture on optical lattices, if it wants to. No? So I remind you what was this kind of program. Yesterday we did a little bit of introduction, going through the light shift, discuss a bit with the experimental configuration of using light interferences to create an optical lattice. And by the way, do you mind if I remove the mask? Okay, thanks. I am vaccinated and I also got COVID. So we did this introduction to optical lattices, and what I would like to do, we discuss the special case where we pulse the lattice, or when the atoms are flying through the optical lattice, so with a short interaction time between the light and the atoms. And so what we'll be doing now in the next 3 lectures is to consider a stationary lattice, and we put atoms into this stationary optical lattice. So today it will be mostly about non-interacting gases. And so I will briefly go through Bloch theorem and Bloch wave functions, just to remind you how it works and how one can calculate the band structure for non-interacting particles and the typical type of properties that these bands have. And then we will discuss a little bit about what happens when you put non-interacting bosons or interacting fermions in those optical lattices, and how we can measure some of these properties in experiments. So I will also discuss some experimental techniques, some of which you may have already heard about in previous lectures, like time-of-flight techniques, but in optical lattice it's slightly different. And then some which are more specific to optical lattices, like quantum gas microscopes, for instance. Okay, so let's start. Let me do this. So I have a stationary lattice, and this will be always there. So I will, let's consider the 1D case, and I will write Vx V naught sine square of kx, as we wrote yesterday, and I remind you V naught is S times the recoil energy. So to describe the type of wave functions and eigenenergies in such an optical lattice, what we have is this celebrated Bloch theorem, which I assume you already all know, or at least have heard about. And this tells you that the eigenenergies can be written in such a way, eigenfunction, sorry, a phase factor QR times a periodic function. And so I will just walk through this, quickly through how one can convince oneself that it is indeed the case. It's relatively easy, and I will not detail everything, but just remind you how it works. So what we are considering is an Hamiltonian, which is that of a non-interacting particle. So it's p squared over 2m plus this potential Vx that I want to describe. And what I want to know are what are the eigen vectors, functions of this Hamiltonian. So let me so this is my optical lattice, and I will call this elementary vector A1, And okay, I will deal with a 1D lattice, but of course, I mean, we can, and I'm dealing with a square lattice in this simple example I'm doing, but it can be of any structure. Then I can have, if I have a 2D lattice, A2, and so on. And so let me write vector A, which will be just like a composition of the elementary vectors on the lattice with, so N1, A1, into 2, A3. And so why am I interested in this vector? Is that it's, of course, kind of special. I want to use the symmetry of the lattice. So you know that if I do a translation by A, of course, nothing changes. Well, the wave function. I mean, if I have this infinite lattice, the wave function should be the same. So a translation by A can be written E, A, P over H bar. So this is the translation. So it's an operator. You have the momentum operator, and A here is just a vector. Okay, so this is one, let's say, operator that is associated to the symmetry of my crystalline structure. So the one thing which is special is, so of course, well, first of all, why do I introduce that? Well, I will just said, this operator is that of the, sorry, I'm treating the 3D case where I said I would do a 1D one. Okay. So of course, this translation operator commutes with the lattice because it is its symmetry, and it also commutes with p square, right? Because it has only p there. So this means that it commutes with the Hamiltonian. So what we'll be doing is looking for eigenfunctions, which are so this psi, they are of course eigenfunction of H, because this is what we want to solve, but they are also eigenfunction of this translation operator. Good. So this is one property of our wave function, is that there will be eigenfunctions of this translation operator. The second point is that, of course, if you look at the Hermitian conjugate of this translation operator, we get a minus sign. And what is the effect of translating by minus A? It's exactly the reverse operation of translating by A, which means that TA dagger is identity. This is trivial, but this is important because it means that I can write eigenvalues so eigenvalues of TA, but of H, where we are looking for both. I mean, they are the same. Like E theta j, right? Just like we have modulus 1. Okay, so this is the first property that one needs. Now, what we will be doing is to consider the so-called reciprocal lattice. So what is this? It's just the lattice such that so there will be, sorry, let's say B1, B2, and B3 such that Bj Aj prime is 2 pi delta j j prime. So it's the reciprocal lattice of the one I'm considering. And so this is in momentum space somehow. And so I will introduce a momentum Q that I will write in this decompose in this reciprocal lattice. And I want to use a special Q, which is the one for which lambda is associated to this eigenvalue. So I will write, I want 1 over 2 pi times theta j bj. Okay, so lambda j is theta j over 2 pi. And this will be, of course, well, the Q which will give me the phase in the eigenfunction of a block wave function. Well, let's make just a comment here. Of course, if you change, if you have one theta value, and you increase it by 2 pi, you get the same eigenvalue, right? And so therefore you will get the same eigenvalue and the same eigenfunction. So this Q vector here is, let's say, well defined only if these lambdas are within pi and minus pi and pi. Okay? And if these lambdas are outside this, then we will get exactly the same solution, same eigenfunction, same eigenvalue. So the lambda j, you can keep them in, and this is called the first Brillouin zone. No, sorry. I put 1 over 2 pi here, so with the definition I did, this is between minus pi, and so this is 1/2, minus 1/2, and 1/2. Okay, so let me notice that if I look at the projection of this vector Q on the lattice, one of the lattice vector, what do I get? Well, it's only non-zero for bj, and if it is equal to theta j. Which means that, you see, the eigenvalue, instead of writing just exponential with theta j, I can write it exponential q times aj, which starts off looking like exponential EQR. Good. So this was the second step. And now let's look for the last step. So I have a given vector Q. I have the eigenfunction of my Hamiltonian H. And what I want to show is that I can indeed write it as proposed by Bloch. So let me consider a translation of this function. Well, let me take this one as well. So just to consider exactly the same phase here. So this is a translation by Aj of of this function. This I wrote nothing. But we said that CQ is also an eigenfunction of the translation operator. And if I look at the translation along AJ, this is exponential I theta j, which is therefore EQ AJ times the eigenfunction. Okay, it's just putting together what we have said so far. Okay, so you see what I've been doing is first showing that since I have this translation operator, which will be also, the eigenfunction of the Hamiltonian will be also those of this translation operator, then I know that I can write the eigenvalues this way. And then what I did is introduce a wave vector, like a momentum q, which I can write this way, and therefore express the eigenvalues of this translation operator or the Hamiltonian as an exponential of a scalar product q aj. Okay, so this is, we are almost done. Now remind you that what the Bloch theorem was telling us is that I can write the wave function like this phase times a periodic one. Okay, so what I would like to do now is to know whether this function here, this IQ R, is really periodic. So what I will be considering is exponential E minus Q R times CQR. This is the one. This is equal to UQ, and this is the one that I would like to show that it is indeed periodic. And if I find that it is periodic, then it's fine. It means that this form is correct. Okay, so this is kind of simple. I can look at EQ R minus AJ, for instance. So I get E minus Q R EQ R AJ times psi Q R minus AJ. And you have it written here. Now there's a sign problem. You see, what I wanted is to get. So of course, what I want is I want this thing to be equal to psi QR. So what is okay, so I have a sign issue between here and here.
You translated the minus a, so you get a to the minus a.
What you're saying, that there should be a minus here?
Yes, because you translated the minus a.
Okay, I trust you. I'm in front of the board, so it's always okay. Fine. And you see that, of course, this exponential EQR times this function psi q, it's UQR. And so we've shown that indeed it is periodic with any elementary vector of the lattice. So this is the Bloch theorem that one can look at eigenfunctions of this kind. So I guess you already all knew that. That was just a short reminder without taking too much time. And so now I would like to have the bond structure. So which, what I mean is to be able to calculate the eigenvalues of this psi of these Bloch functions. The eigenvalues, sorry, eigenenergies. Well, yes, whatever. So to do that, I stress again that what we are looking at, it's a problem where we have our atom in with a given momentum k, momentum p, for instance. And in the lattice, we will have these two photon transition, absorption and spontaneous stimulated emission, sorry, ending up with the atom getting an extra 2h bar k momenta. So I already said yesterday that this is important to keep this in mind. Once again, I'm stressing it. Remind you what the lattice does is to couple our atom to discrete momentum states. And this is exactly because we are coupling to discrete momentum states that we will be able now, I mean, the way we solve the eigenenergy is basically based on that. So let's say, to highlight this somehow in the lattice I'm considering, which I remind you I wrote it sine square kx times v naught. This is v naught over 2, 1 minus cosine of 2kx. And so I have in this cosine the sum of these two exponential, which directly relate to this getting a plus 2h bar k or minus 2h bar k. So it's 1, I should put a 1/2, well, exponential I 2kx minus 2kx Okay, so you see I'm just like emphasizing the fact that in the lattice potential, in the interaction, I have these two terms that relates to getting 2h bar k or minus 2h bar k. And you will see now why I'm doing that. In a second. So the idea is the following. You take your beloved Bloch function, which we said we can put this way. And u is a periodic function. So I can decompose it in Fourier space. How do I call this? Alpha j. Q, well, I will drop all the e to 2 pi e. No, if I put, no, okay, so, oh, sorry. This is a j and a kx, yes. So I write this, I decompose this periodic function in this discrete momentum space. let's go to the 1D case. It's going to be easier. Sorry, I'm always oscillating, but IQX. Why? Because I mean I want to put this inside there. So what do I have? I have IX times Q plus 2KJ. Okay. And I remind you that what I have, the Hamiltonian, is P squared over 2m plus V, and I want to calculate the eigenvalues. This is what I want to find, right? And so the reason why I'm decomposing the block function in this discrete momentum basis is that you see that now this guy will add a 2kx to the phase of this one. And actually this will amount to change the value of j. And so what I will end up with is, for this equation of the eigenenergies, I will just write an equation on the alpha j's, these coefficients. And then it will only amount to solving this equation. Okay, so what do I have? Well, I have the p squared over 2m that will give me something like plus 2kj squared divided by 2m with the associated, let's say, alpha j. Then I have another term with alpha j, which is the potential, it's plus v naught over 2. This was the first part of the potential. And then we have two other terms, which writes v naught over 4. And these two, they change. Ah, yes, I've cancelled it. They add or remove a 2kx. Okay? So this amounts to changing j by plus 1 or minus 1. And so therefore, I will get alpha j plus 1 plus alpha j minus 1. And so this is equal to, sorry, I don't know where I put an x here, EQ times alpha j. So I have a set of discrete, a discrete number of equations with these coefficients alpha j and the eigen energies. And of course, I will not solve that on the blackboard. Then you solve it numerically. But it's really, it's really easy to play with these sets of equations. And of course, you want to solve this numerically. The first question to ask is, how many equations should I put in? And typically, if you take j between, let's say, 10 and minus 10, you get results which are relatively accurate. So this is typically, let's say, 10 to the minus 3 accuracy for the energies. Well, it's one order of magnitude, eh? And if you put 20, you get about 10 to minus 6. Okay. Well, by the way, it's a good exercise to do it, at least to do it once, and then to play. I will show some numerics just to feel a bit how these things work. So do you have any question on this? Fine. Okay. So the first thing that I want to discuss is the fact that we said in the presence of this lattice we want to work. Eigen functions and eigenvalues are well defined over the first Brillouin zone, and which is, let's say, between -1 and 1 in those units. And so if you take the eigenenergy of the particle without the lattice, which is just simply, of course, h bar k square over 2m with no lattice, this is the parabola which is plotted here. If I want to fold this parabola onto this first Brillouin zone, this is what you obtain. So I guess you have already seen that. And you see that there it starts to look like a band structure. And so when we put the lattice, this happens. So I've put here like four different values of the amplitude of the lattice in recoil energies. Right, S is this amplitude in recoil. Over the first Brillouin zone, you have also recoil energies in the vertical direction. So what do we see? Well, we see that we have several bands. We see that they change shape when we change the amplitude of the lattice. Typically, we see it here, the band gets flattened as the lattice amplitude is increased. And you also see that we have energy gaps which are appearing on the edge of the Brillouin zone, and these energy gaps are also increasing with lattice amplitude. So let me zoom in. So this is for one recoil. So I'm zooming in this small part here, so at the edge of the lattice. In dashed, you have the parabolic dispersion of a non-interacting particle. And in red, this is red and red, while here it was red and green. So you have the lowest band and the first excited band, and you see that there is a gap which opens. If you are looking at a 1D lattice, the gap opens as soon as you have a non-zero lattice amplitude. So actually, I put here 1, but I could have put 0.1, and we will still have seen a gap, of course, of smaller amplitude. But as soon as you have the lattice, you have the gap. Let me stress that this is not the case as soon as you are in 2D. Because now the lattice, the band structure is also two-dimensional. And so you have gaps which are opening along the axis of the two lattices. But if you would look at 45 degrees, that the bands still touch each other. And I will just show you in the 3D case. So what is plotted here, it's as a function of lattice depth, the energy. And what is plotted is the energy occupied by the band. So what I mean by that, so for the first band, it's this energy scale, so all the energies which are occupied by the band. For the second band is this energy scale. So this is what is plotted, okay? Those width here, the bandwidths, which are plotted as a function of a lattice amplitude. And so you see that if you are considering just the 1D band structure, as soon as you put a lattice, as we were saying, all these bands, they separate, because you have a gap which opens as soon as you have a lattice. If you look in the 3D case, the situation is very different. Because, so as I said, you have different directions where you can look at your lattice, and you can look. So 1, 1, 1 means you look at the momentum vector that corresponds to 1 in the direction of the lattice x plus 1 in y plus 1 in zeta. So you are looking, well, in between the three lattices. I don't know how I should have said it. And you see that these bands here, they overlap with this one, for example, 2, 1, 1 or 3, 1, 1, up to a relatively large lattice amplitude. Okay, so keep in mind that, well, actually, I could have shown you a two-dimensional at least band structure. Keep in mind that although you have a gap which opens along the lattice direction, then if you look, for instance, in 2D at 45 degrees, this is not the case as soon as you put a lattice. You need a larger lattice amplitude to really have these bands separating in energy. So in 3D, it's typically around 2.2 recoil for a square lattice. Yes?
Just to clarify, you mean that there is no gap in the escape, but do you still have a crossing of the bands, or no crossing?
No, they are touching. Yeah,
Huh?
they are touching.
They are touching, basically.
So they, well, I will, let me show you a picture this afternoon. If I try to draw it, I will. So, but you have most probably already seen it, where you have these bands. So you have a blob like that, which ends up with being like the edges, the corner of a square, and you have those two things which touch on the corner, but not along the lattice. So I don't know if I should have shown you a picture indeed. So how should I? So this is the direction x. This is the direction epsilon. So along this, so this is the first excited band, and this is the lowest band. And so if you look here, you have like a separation of these two guys in energy, but they are touching on the side. So is it clear? Yes? Okay. Yes. Let me comment just a little bit the shape of the lowest energy band, because also we will be using it a lot in the following lectures. So here it's plotted this lowest energy band with energies which have been, the energy band has been normalized to 1, and the energies have been shifted. Because if I look at increasing lattice, the band flattens and changes offset. But what I want to stress here is the fact that, so in blue you have the parabola of a non-interacting particle. And if you increase the lattice amplitude, then you get towards this cosine function, which is, so the black case, it's this sinc square. So for s equal 100, it's extremely good. But already for s equal 10, you are very close to having this sinusoidal dependency of the energy of the lowest band with the quasi-momentum Q. So this is something that we often use. And by the way, the bandwidth, and we will introduce this J factor, which is the tunneling amplitude this afternoon, the bandwidth is 4J. The second comment I want to make on these energy bands is that if we look, so this is, once again, the band structure for an amplitude of 5 recoil. If you are in this regime, like 5 recoil typically or above, then the bandwidth is much smaller than the gap. So the bandwidth, sorry, of this lowest energy band is much smaller than the gap to the first excited band. And so therefore, it is relatively easy to actually have, if you want to play with atoms, to load them in this lowest energy band and completely neglect any excitation to the higher bands, okay? Because it's really far away. And so this is what we call the time binding regime, and we will be discussing this afternoon the case of bosons, and on Monday a bit the case of fermions in this regime of deeper optical lattices. Okay. So I would say that this is kind of the summary of this band structure. So eigenenergies as a function of quasi-momenta. So I've put like first, second, third Brillouin zone, but as you know, we can fold everything onto the first Brillouin zone, as we've just seen. And so what do we have? Well, we have, first of all, instead of having this parabolic shape without the lattice, we have a band structure with different bands on the first Brillouin zone. We have energy gaps between the bands that open. And we have a band structure which typically go from something which is initially parabolic without the lattice to more and more flattened bands. So, I mean, somehow, if you keep this in mind, well, you have all the key ingredients to understand lattice physics for non-interacting particles. Okay, and just to finish, some block wave function, because you can also, of course, get the eigenfunctions. So n here is the number of the band. So n0 is the lowest energy band. This is the first excited band. N equals 2, it's the second excited band. And you have block functions, which are plotted for lattice amplitudes 2, 8, and 20. And two different quasi-momentum. So one which is at the center, 0, and one on the edge of the first Brillouin zone. Well, so you see that this guy here looks not so far from being a plane wave, right? While the more you increase the lattice, the more you localize the wave. And then you have also, well, yeah, this type of waves in the excited state. But anyway, I will not be discussing what happened in the excited bands. Although there are many, I mean, nice experiments in these excited bands, for instance in Hamburg, but I will not have time to discuss them. Okay, so we have this band structure, and we want to play with our atoms and to load them, of course, in this band structure. So how can we load the atoms in this optical lattice? And there is one question. If you want to load the atom in the optical lattice, which kind of comes naturally, especially if you want to study low energy physics, is how can I do an adiabatic loading? How can I load the atoms in the optical lattice without heating them up, without changing the entropy of the system? So this is actually a very, very difficult question. I don't have an answer. It's already very difficult in the case of non-interacting particles. Well, simply because, you know, I mean, except solving some, I mean, if I want to have like some kind of analytical solutions, well, I know how to solve the harmonic oscillator, but this is not a harmonic oscillator problem. And then I can do some perturbation theory. But I mean, apart from that, I will rely on numerics. So this is the first point, which is it's not easy to get a picture of how to describe the adiabatic loading. And then a second point, which is even much more difficult, is that if you consider that the system is interacting, then, I mean, it's really difficult. So I can do two things. Wow, I'm a bit. At what time I started? At 9 or a quarter to 9? At quarter to 9. Yeah. Well, I would like to just to give you one example of how you can try to treat this problem with perturbation theory. But of course, as I said, it will be restricted to a to a perturbative regime. But still, just this will give you a flavor of how one can do it. And if I ask you to guess, so what I will be doing is trying to say, well, I want to load, typically I want to have the atoms in one block wave function, okay? So, and change the lattice amplitude so that I'm staying in the same state, so not excited towards higher bands and things like that. According to you, what will be the typical time scale with which I need to compare how to increase the lattice amplitude?
The size of the gap? Oh, no, actually.
Yes, it could be, but actually it's something even much more simpler than that. Because I will be doing perturbation theory. Now, I'm just saying that there is one energy scale in the problem, the recoil energy. So, I mean, what you will end up is you want to add a latch shift, which is of the order of the recoil energy. You will end up saying that you need to go slowly compared to this time scale, I mean, h bar over recoil energy. It's always like that. Especially because, if you do perturbation theory, it's sure that you will get this type of results. Okay, so let's discuss this loading doing perturbation approach. So the one thing you need to remember is that if you have an Hamiltonian that you parameterize with a function lambda, which is let's say lambda over t. So typically, I want to increase the potential V, so I will change this coefficient, like let's say from 0 to 1 over time. If you assume that you have, let's say, eigenfunctions that you know at each time, okay, so this is an Hamiltonian, and at each time, so I change the coefficient in front of this potential I want to raise, and at each time I know what are the eigenfunctions, then what you should ensure to have adiabatic loading is that the derivative, time derivative of the projection to, let's say, 1 phi n onto phi n prime, this is much less than the difference in energy between these two states. So this is kind of, well, you can obtain that. I don't know if you've already seen this. If you do, well, once again, perturbation theory, and then you find that, well, this is done in the way I like it is in the books of quantum mechanics of Sakurai. Okay, so I want to apply that to my problem. So what we said is, what we have is we have a block wave function. So I will, how do I want to write them? And I will consider, so only the lowest energy band, so I drop the index. I drop the, well, no, I wrote it psi before, I think. Psi q naught, sorry. I need to recover what was the. Okay. So what I will do is the following. I have the atoms, which is, let's say, in the state G, that means ground state, and with a vector momentum state Q naught, and I want to increase the lattice. So what will do the lattice? It, of course, couple these guys to something where I have plus 2h bar k and minus 2h bar k to first order, right? So I can do this two-photon transition once again. So, and I can say the following. So let me drop the J. It's going to be easier. And I consider like a superposition of these two guys. So of course, the energy difference here is associated to this 2h bar k momentum, so it's 4 times the recoil. And the coupling that I have here, so I remind you that V, it's V naught divided by 2 minus V naught divided by 4, and the terms which give me 2k minus 2kx. Okay, so in this coupling here, the amplitude will be lambda V naught divided by 4, right, to get the 2h bar k or minus 2h bar k. So what I will be doing, well, let's say that I do second order perturbation theory. So when I start putting the lattice, so at the beginning, the atom without the lattice is in P naught. And when I start putting a little bit of lattice, so what do? There will be a small like mixture of this state onto the initial state. And second order and perturbation theory tells me that the state is modified by the coupling of the two states divided by the energy difference. Yes. Times, so 2h bar k plus minus 2h bar k. Okay, so this is perturbation theory. Sorry, I put a 2 here, it's a 4. So this is when I want to load how my state at initial times should evolve, getting an admixture of these higher momentum components. And now what is the question? Well, what it is that I do not want? What type of process I want to avoid? Well, this very type of process, in the sense that what I want is to add a small admixture of this to the initial state. But what I do not want is to have a real change of the state from here to there. Okay? In perturbation theory, I just want to slowly add up this guy, but I don't want to have like a real change of a state. So what I want to avoid is to have a transition which is the one that the lattice can do, of course, but this is the one I don't want, is to really have a transition from this to, let's say, well, sorry, so this is a Q naught, and here I'm missing Q naught plus 2h bar k, and Q naught minus 2h bar k. It's incredible how once you are like just on the blackboard, you can just forget terms. So I want to avoid this kind of transition. Because once again, the only thing I want is a small like admixture. So for the adiabatic condition that I wrote before, this is the kind of two states I want to compare. So what I want is to compare Q naught plus 2h bar k plus Q naught minus 2h bar k. Well, 1 over square root 2. So this is what I called phi n prime. Then I have this guy here. This is the one I want to follow. And so this overlap, so the small change that I add to psi q naught over time, this small change, I want it that its projection onto the real transition that I can do to be very small as compared to the difference in energy, which is 4 times the recoil. Okay? So once again, the idea is what you want is to add this small mixture, a little by a little. And what does mean the little? It means that this term here, its time derivative, should be small compared to the energy difference. And so you see that what I will get is a lambda derivative of lambda times V naught divided by 16 ER. There will be a square root 2 here as well. Okay, so it's this amplitude here. That must be smaller than for here. So this gives me a condition. And of course, as we were discussing, what we get as a scale is the recoil energy. So let me assume that I will do the following. That over time, lambda will be like that. I start from 0, and over a duration tau, I increase lambda to 1 in order to raise the optical lattice. And actually, I also need V naught to be, let's say, not of a large amplitude because I'm using perturbation theory. And typically what you get, what did I got, was that you want this tau to be greater than 32 square root 2 h bar V naught divided by ER square. Okay, so this gives you a typical duration, right? So once again, this applies only at the early times when I'm just like trying to raise up a little bit the lattice. And so what you typically get, so I used V naught equal the recoil and sodium atoms, and what you get is that you want this duration to be larger by 0.2 microsecond, which is actually relatively short. And in practice, if you do this, it will not be adiabatic because of other problems like interactions. So you see, this is kind of academic derivation. So it gives you a taste of what you want to do, right? You don't want to, you want to add this admixture to the initial state slowly. But I mean, of course, this type of derivation is restricted to only like the small lattice amplitudes, and it may not be what you want to actually do in the experiment. But still, okay. So there is one another approach that maybe I will talk about this afternoon. But again, it's not a very good one either. Conclusion. Well, we need to try in the experiment. Right? It turns out not to be easy either. So there were several attempts. So in the early days when people started using optical lattices. So in this experiment that was performed at NIST, so they were ramping up a lattice with an amplitude that goes up linearly and then ramping down, and trying to measure how many atoms were left in the 0 h bar k component. So they were starting with a BEC at rest and then look at what happened. So you see the time scale is a few microseconds. And what you see is that if the ramp is relatively of a small duration, then you can lose quite a lot of atoms in the 0 h bar k component, which means that you have excited a lot of atoms. So you have put atoms in the higher bands, provided these 2 h bar k's or 4 h bar k's and so on, which is what we wanted to avoid. And if you use longer time scale for the ramps, then it looks like you're going towards a better adiabatical loading of a lattice. But so as you see here, it's not that close to 1 either. So then there was some visibility measurement a little bit later, and we will come back to this type of measurement, what it means. So it's basically probing the coherence of a gas somehow. And you have this visibility as a function of the ramp time once again. So now you see that time scales have increased quite a lot. So this is rubidium, this was sodium, but so it does not change that much. But here you have interactions, and it's a three-dimensional system, while here it's a 1D lattice with a diluted gas. Well, time scale of this order, and you see that it looks like there is some kind of plateau if you use a ramp which is long enough. So it kind of, this is the best you can do somehow. So why is it complicated? Because in the end, what you could do is something, for instance, as stupid as this. You start from a BEC. So this is, well, these are pictures from my lab. So we use an optical dipole trap. You load the lattice, remove the optical dipole trap, and then you do the reverse. And what you want is to be fully adiabatic, meaning you keep the same atom number and the same energy. What is the issue? The issue is that, well, you see, if you see those two pictures, if I would not put the numbers there, well, it's all saturated, so I'm cheating, of course. But you could say, well, there is no thermal fraction around the BEC. I mean, it looks like really cold. You have not heated up the gas. I mean, I think this is up to 30 recoil in 3D, so it's a deep lattice. Well, the issue is that you have lost some atoms. And then you cannot tell anything, because maybe these atoms have been lost carrying a lot of energy. So even though you lose like 10% of the atom, and of course, I mean, these are single shots, so there is also like the shot-to-shot fluctuation of atom from one run to the other, from just technical reason that you would have some atom fluctuation. So actually, this atom fluctuation is just a factor 2 larger than the one we have on the experiment. But still, the point is, even if you have lost 1% of the atom, maybe this 1% have taken out some energy, and this is not, I mean, this is not isentropic anymore. So it's really difficult to really find out a way to quantify this adiabaticity in the experiment. Okay. So with that, I would like to just briefly now comment about non-interacting bosons and fermions. So you've heard about what is a Bose-Einstein condensate in a harmonic trap early this week. Well, if you put, you can put a BEC in an optical lattice. So this is the lowest energy band. I've kind of represented the wave function of the BEC. So it's very narrow in momentum. This is the ID, and it's a coherent state in so in this Q equal 0 momentum state, exactly as the coherent state you've seen this week. So it has similar properties that the ones you know in a box or harmonic trap. And then, of course, you can also have thermal clouds of bosons. And if temperature is less than the energy gap, they are mostly in the lowest energy band, and they will extend in the lattice. Okay, so now how can we probe a bit of those properties? So the first thing is, I would like to discuss a bit time of flight. Wow. Do you all know what is time of flight experiment? Yes. But well, I would like to pinpoint one thing. So you know that in time of flight, the idea is you have your gas, you let the atoms fall, and you measure a position after the time of flight, which you say, well, if this position is much larger than the initial extent of a gas, this will reflect somehow the initial velocity of the atom. And you will use a ballistic relation to say that, so r divided by t of, this is a velocity, times m, this is equal to h bar k. And so you get the momentum k from measuring the position after a given time of flight t of. Okay? You are all familiar with that. Well, what is the condition to actually get time of flight correct in order to, if you claim that you want to measure the intrap momentum distribution with a time of flight experiment, actually there are some conditions which are not always fulfilled, if not almost never in experiments. So, well, okay, the first one is that you need to have no interactions, of course, because this ballistic relation, if you have interaction during the time of flight, I mean, this is not true anymore. Okay, so this is obvious. And now the question is, how long you should have a time of flight? Well, let's consider thermal bosons. So you know that their dispersion in energy, in kinetic energy, is related to the temperature. So what you want is that for typical velocities, which will be of the order of kt over m, right? This will be the typical order of these velocities. What you want is that v times the time of flight to be larger than, let's say, the distance of this is the r naught, which will be intrap size. I mean, this is the idea we've done here. And if you are in harmonic trap, then, I mean, this is also related to the initial size with the trapping frequency. And so what you get is omega t of larger than 1. And this is often what people use to say, well, this is a long time of flight to get the initial momentum distribution. But this is not correct. And the reason is the following, is that if you have some phase coherence in the trap, and I have a phase coherence length, L phi, then this gives rise to velocity velocity fields, which are the order of h bar over m L phi. Okay, this is typical scale on which I will have phase fluctuations and phase coherence. Well, now if you plug this there, the situation changes dramatically, because what you get is h bar over m L phi times t of being much larger than r naught. So t of much larger than m L phi r naught divided by h bar. So if I have a phase coherence, this is the condition I need to fulfill. By the way, this is strictly analogous to if you do diffraction in optics. When you enter the Fraunhofer regime of diffraction, what it means is that the quadratic term in the phase factor is negligible compared to the linear one. And this is where you have the Fourier transform. It's exactly the same condition. I'm talking about a non-interacting matter wave, so it's exactly the same, of course. And just if you take those guys equal to 20 micron, for instance, and you use rubidium, then the time of flight needs to be much larger than 0.5 second. So there is no rubidium experiment which is doing a time of flight which is much larger than 0.5 second. Of course, if you have a smaller mass, it's easier. So if you do the same thing with lithium-6, so this is rubidium-57, what you get is something like 40 milliseconds, or something like that, yes. So it's much easier. So of course, the point is, if you don't care about fully resolving the velocity components associated to this phase fluctuation or this phase coherence, this is fine. I mean, you can do a short time of flight and you will learn information about the momentum distribution, but you will not strictly get all the information. Okay, so keep this in mind. So what do I do now if I do this time of flight from the lattice? Well, I have this quasi momenta, h bar q in the lattice. And when I will switch off the trap abruptly, so let's say I have, so here it's a 3D lattice with these red arrows, right? I switch off abruptly the optical trap. Then I project this q onto the plane wave basis, and I get different components. Okay? So if you have a BEC, well, it doesn't work, which is phase coherent, and you put the lattice, you will see sharp diffraction peaks, which corresponds to these higher orders. So these are absorption images taken, so you see like, so without a lattice and a different lattice amplitude. So once again, you can draw an optical analog in the sense that you can take some slits and you put a coherent wave. And then what you get in the diffraction are peaks, which are related, of course, I mean, their spacing is related to the spacing A here. Their width is related to the width of the slit. No. Now it's related to what is this size here. And the width of the slit it gives me actually a modulation here. How do I call that? Small d. And so this is the reason why you get only like you see like you start to see those peaks here, but their amplitude is much less than this guy, just because you have the shape, which is the convolution of the distribution of in the trap. Okay. Well, I guess you all kind of know this, so I go fast. What about fermions? Well, you know that we have Pauli principle and we fill up bands. We'll fill up the bands, and so of course then it will depend a bit where the Fermi level is, whether you have like some metal, if Fermi level is within a band, or maybe if you have a Fermi level within a band gap between, let's say, the lowest energy band and higher energy band, then you will have some kind of band insulator. So, in the case of fermions, one of the things you would like is to, well, also you may want to do that with bosons, is to understand and to measure in the experiment what is the population in the different bands, to kind of see whether you are filling the lowest band or having also some fermions in the conduction band and so on. So there is one technique which is called band mapping, which is relatively easy to understand. So you start from this picture, and this is what happened, so the energy bands in the presence of a lattice. And these dark dots here, these are fermions. So I filled all the lowest energy band and put some in the first excited one. Okay? So if I unfold that, because I will do a time of flight and project onto plane wave basis, this is the picture that I have. Okay? And so now what I want to do is not to project all these guys onto every momentum states, as we have just discussed before, but to somehow smoothly close these energy gaps and ending up having the atoms staying at the same, let's say, ending up having the atoms with a real momentum that reflects the fact that they were in higher bands in terms of quasi-momenta in the trap, or in the lattice. So you basically need to decrease the lattice amplitude, not so fast, with respect with the band gaps. If you, as I wrote here, if you have interactions, you want to avoid having interaction somehow thermalizing and mixing up the momentum states. So typically, this band mapping, you want to do it slowly compared to the time scale associated to the energy gaps, and fast compared to the time scale associated to interactions, so that interactions are not messing up. Okay, and so this was done with bosons in as early as 2001. So here you see bosons which were heated up only in the lowest energy band, so that they occupy the lowest energy band, but they were not excited to higher energy bands. And so you nicely see the square Brillouin zone associated to a cubic lattice. And here they were exciting a lot the system. And you see, so I've put these two lines. So this is the first Brillouin zone here, and you see the population in the different bands, and you see the different bands which are really appearing in the in this technique of band mapping. And so this is something with, an experiment with ytterbium, fermionic ytterbium in Florence, where you also see nicely this lowest energy band. So let's go back to the fermions. And let's do the band mapping. So this was done by Esslinger's group, so some time ago now. And what they were doing is increasing the number of atoms, so filling up the band. And of course, at the beginning, you have like only a small number of fermions, which are located at the center of the Brillouin zone. And this is like a conducting state. And you increase, and you see that you start filling up entirely with those fermions, the lowest energy band, and you get band insulator. And they were also measuring, so this is a profile, a cut through this image. So population as a function of quasi-momenta, and you see that it's not so bad, not so far from having like this square shape you would expect for a perfect band insulator. Okay. So, these were like first experiments, and now techniques have evolved to image these lattice systems. So the first one I want to discuss a little bit is so-called quantum gas microscopes, which were really a large improvement in the community to get new quantities. So let me first mention this work in the group of Chengqin in Chicago, where actually they were in 2009 capable of measuring in situ atomic distribution of a lattice Bose gas, which is not yet single atom resolved, but still, they were capable of really measuring nicely the density in the trap, in the lattice. And so just at the same time came out those so-called quantum gas microscopes. So the feature of this microscope is that they are capable of resolving each lattice site and to tell whether you have or not an atom in a lattice site. So you can see that you have this discretized, and you see square structure here. So this is from the Greiner group at Harvard, and this is from Emanuel's group in Garching, which is similarly, and you see like each tiny red dot here, it's a single atom. So with that, you are capable of saying where the atoms are side by side. So this opens the way to a new set of experiments where you can look at site occupation, correlations between atoms between different sites, what is the atom fluctuation on each site, and so on. So it's not perfect yet, and let me just tell you a little bit more how it works. So the idea is you have a large numerical aperture, so you put your, so it works with a two-dimensional gas, which is represented here by these small red dots. And what you are doing is, while the atoms are in the lattice, you make them fluoresce and measure the fluorescence. Okay? And you need so large numerical aperture to get them. But of course, if you try to have a shallow lattice, and you want the atoms to do some fluorescence by shining some light they absorb and then re-emit, they will of course get a recoil energy when they emit a spontaneous photon, right? And so if it is a shallow lattice, the atom will move. And so you will not be able to actually say where they are. So in all these experiments, well, they prepare somehow something before, then they load the lattice, they do the lattice in the physics, the one you want to study, and to image, they ramp up this so-called pinning lattice. And as its name is saying it, you are trying to pin the atoms in the lattice site so that once you have them fluoresce, they are not moving around anymore. So this is the amplitude of this spinning lattice, 5,500 recoil energies. So the lattice typically, I mean, where the physics is interested is like from, let's say, from 0 to 30, 35 recoil. And you see that to have this fluorescence and to measure the atoms, they ramp up a huge optical lattice. Where, of course, here you have no tunneling at all from one side to the other. The atoms are really pinned. So the first thing is that so you shine some light so that they absorb and fluoresce, and you also need to cool them a little bit because otherwise, after many fluorescent cycles, then they could still leave the lattice or move around, being heated up. And there is another, let's say, issue associated with this technique, at least for the boson. It has been, let's say, with fermions, we will see that it's a bit different now, at least in one group. But with bosons, you have like this huge optical lattice, the pinning lattice. And the point is that if you have two atoms in the same site, you have really extremely large light-assisted collisions. So you basically end up with no atoms. Okay, because of light-assisted collision in this extremely deep optical lattices. So what does a quantum gas microscope do, at least for the bosons, as I said, it's a bit different for fermions, is to measure the parity. So you can measure whether the sites were occupied by 1, 3, 5 atoms, or by 0, 2, 4, and so on. Because if it is even, you will get 0 in the end. If it is odd, you will get 1 atom in the end. So this is the type of fluorescent signal. So this is the number of counts on 1 pixel of well, actually a few pixels of a camera that corresponds to a single lattice site. And you see that the number of counts has this double shape, which then allows you to tell, well, if the number of counts is below this threshold, this means that I have 0 atom in the lattice. And if it is above this threshold, it means I have 1 atom in the lattice. And this is the way you can discriminate between 0 and 1. Okay. So I have 3 minutes left. Let me tell you about another technique, which is also single atom resolved, which is the one we've developed in my lab, and which now is a technique where we detect each individual atom not in the optical lattice, in position space, but after a time of flight. So we are working with metastable helium, which is even lighter than lithium. And the time of flight is like 300 milliseconds, so we are deep in the regime and really fulfill this condition. And so the trick here to be able to see atoms one by one is because metastable helium atoms, they have 20 eV of energy in the state where we manipulate them. So it's not the ground state. And helium, it's a noble gas, right? So to excite it, you need a lot of energy. So even the first excited state is really lying far above the ground state. And 20 eV, it's an energy which is large enough that if you let fall one atom onto a piece of metal, it extracts one electron from the metal. Atoms going, of course, to its true ground state. And so this is what we are doing. So we get a first electron, we amplify it, and then we have a technique to be able to tell. So this is the type of, let's say, metallic plate I'm talking about. It's called microchannel plate. And then we are able to also tell what is the position in the X and Y direction of the detector, along with the time of arrival. So for each individual atoms, we have 3 coordinates that allows us to rebuild, assuming ballistic relation, the 3-dimensional momentum of this atom. And so this is a picture of a Bose-Einstein condensate, so in a 3D square, 3D cubic lattice. So each tiny blue dot is a single atom. And these different patches, these are the diffraction peaks that we have already seen in the 2D absorption images. And let me finish by telling you the type of thing that you can extract from this. So this is the momentum density. So it's a cut through the distribution I've shown you. Momentum density as a function of momenta. So you recognize the peaks here, right? Well, this is semi-log scale. I will comment that another time. But I'm showing this because, so now what we can do, because we have the detection of individual atoms, we can ask ourselves, well, what is the probability that in this peak here, which is associated with a condensate, that we detect 2 atoms close by, or that we detect 3 atoms close by, or 4, or 5, or 6. And so we can build these high-order correlation functions, where the small n here means the order, so how many atoms we have. And we can measure that for this, in this region here, which corresponds to the Bose-Einstein condensate. And we have told you that the Bose-Einstein condensate is a coherent state. And so therefore, what you should get is that this correlation Gn, to have atoms close by, should be equal to 1. And so this is our measurement. You see that it's, let's say, equal to 1 up to 2%. Up to, let's say, order 6. So this is the type of thing that you can do if you have a single atom detector, either in situ or in time of flight. You can measure correlations. And just to show you that this is not always the case, to get Gn equal 1, then if you look at what you have in the depletion, what you expect, because it's not a coherent state anymore, it's typically a chaotic thermal state, and what you expect is bosonic bunching. So if you have 2 particles, 2 bosons coming close by, I mean, they like it, and so they bunch, and so preferentially they come 2 by 2. So if you measure the second order correlation function, so which corresponds to this dot here, so this is plotted as a function of temperature, but whatever, what we get is we get something, so this is the amplitude minus 1 equal to 1, so which means bosonic bunching equals to 2. So in the depletion, in the very same set of data, in the depletion, this point here is up there, equal to 2. Okay. So, did I? Yes. Wow. Okay. I'm supposed to stop here, right? So the few things I wanted to add are two things. Well, if you give me 5 minutes, are you okay to stay 5 extra minutes? Thanks. If you would have said no, I would have been disappointed. So the other concept that we can also use in an optical lattice is the group velocity, which you will define exactly as you define it without a lattice. So it's 1 over h bar d divided by k. Well, the group velocity for a wave packet with momentum q naught, centered on q naught. So let's say that this is the lowest band, and so I'm interested in a wave packet with a average momenta, quasi momenta q naught. Then I can define a group velocity like this, as you usually know. Of course, I mean, because this energy is periodic in the quasi-momentum q, this means that the group velocity is also periodic as a function of the quasi-momentum q. Okay, and this comes from the fact that just that we have a periodic structure lattice. The other quantity that we can introduce, which is often used, it's the effective mass. And this is associated to the second derivative, right? It's just like if you think in terms of non-interacting particles, if you derive 2 times with respect with the momenta, then you gain the mass. So you can define the effective mass as, so I will define it, 2 over h bar square, second derivative of E at q naught. No, the 2 goes away because I have the derivative of k square. Okay. Good. Okay, these are definitions. So why do I use those definitions? Well, first of all, because I don't have time to show it, but you can use this effective mass, and in shallow optical lattices, you can rewrite a Gross-Pitayevsky equation for the BEC, replacing the mass that you have without the lattice by this effective mass. And then all what you have been studying, so in harmonic trap or boxes, for BECs, let's say, described at a mean field level, Gross-Pitayevsky, you can apply to it. So, of course, this works at shallow lattices. So just to tell you that this is something we can also observe in experiments, and we will come back to the group velocity just in a second. So this is the velocity measured as a function of quasi-momenta. So you see that it is indeed periodic. So in 2 lattices, like 1.3 and 3.8 recoil. So this was done in Florence like 20 years ago. And you can also measure the effective mass. And there is one thing which is peculiar. You see that you have, this is 0. So you have effective masses which are negative. Well, this is clear because here you have a curvature in this direction. Here it's in the other direction. So here the effective mass is negative. And yes, this was measured as well, which means that this description is correct because I mean this is what you measure in the experiment. So watch that the amplitude of a lattice is relatively small, right? We are talking about shallow lattices here. And now, if you crank up the optical lattice, then you have here plotted the ratio of this effective mass divided by the bare mass. And so let me just say that this type of experiment, you cannot do it in this regime. It does not work the same way because just you can, I mean, this is kind of described by Gross-Pitayevsky equation, and when the lattice is deep, this does not work anymore. It's the tight binding regime that we will be discussing this afternoon with the Bose-Hubbard Hamiltonian. But still, the concept, I mean, you can still calculate that, and the concept of effective mass holds, and it increases if you look at the effective mass. So this is the one here at q equals 0 in the lowest energy band. You see that it increases very much, which means that, well, the atoms are effectively much more heavier if you want to see some dynamics, and this is because they need to tunnel through the lattice. So it's kind of obvious. Great. Last thing, but we have already everything, so don't worry. Block oscillations. So block oscillations, so this was, proposed by Bloch in the 30s. So for real solids, the idea is you take a force, you apply a force, and I will assume it is constant over time. And so, of course, this force will change the quasi-momentum, right? If it is constant, F so which means the quasi-momentum increases linearly with constant force. But we just said that this guy is periodic. So Q, the quasi-momentum of my wave packet, Q, let's say Q naught, I can put a Q naught here, over time will increase linearly with the force, but its group velocity will be periodic. And so you will see a periodic oscillation, because it also changes sign. And so the atoms in the lattice, they are moving back and forth, or the electron in the solid, they are moving back and forth. And the interesting point is that the periodicity is, of course, that associated. Periodicity of this behavior is that associated with the lattice. So it's like QA, which is of the order of 1, right, where A is the lattice spacing. And so this means that over one period, what you will have is the force T A divided by M, which will be equal to 1. So for, let's say, for one period tau. And so from measuring the frequency of a Bloch oscillation, I can get to the force, to measuring the force. And so this is what has been observed and then what is being used. So this is the first observation. By the way, it's in 92, while the prediction was from the early 30s. And the reason why you don't see it easily in a solid is because if you want to have this oscillatory behavior with the group velocity increasing, decreasing, going negative, and so on, what you need is, of course, that the electronic wave function is not modified while it is oscillating in the solid. But I mean, in a real solid, you have defects, you have phonons, and so on. And so it's not like a free propagating electronic wave. And so this behavior is hardly seen. So they actually observed it in some kind of special superconductor there. And with cold atom, it's much more easier because, once again, I remind you, we are creating like a very clean periodic structure. So it's easier, but still, I mean, you have interaction that may play a role. So it was first observed in Paris in the 90s. And then so over like a few period. And then it was realized over like 20,000 cycles. If you remove interactions, which would, of course, dephase, as in the case of electrons, in this group in Austria. So what it is used for? Well, I've just put here two examples, but most probably, I mean, Frank would have better example to provide me with. First of all, measuring gravity. So you put your optical lattice vertically. Gravity is exerting a force. The atoms, they have this oscillatory behavior in the lattice. You measure the frequency of this oscillatory behavior because you can directly see it. You measure this frequency. And you extract the gravitational force. Or you can also use that to measure h bar over m, as it has been done in this paper. So this is just a few examples of use these block oscillations to make measurement. So I've been a little bit longer than 5 minutes, sorry. Do you have questions? No. So it was either crystal clear or you could not follow it. I hope it was the first part. So this afternoon, we will add interactions, and we will be working in the tight binding regime, so relatively deep optical lattices, and introduce the Bose-Bart Hamiltonian and the physics which is associated to it. Thanks for your attention.